we're going to look at 7C. This is in the book, which is now bringing friction into some of the questions that we've been doing. So let's just sort of highlight any key information. Earlier in the module, we saw that the frictional force has to be less than or equal to mu r. So why less than or equal to? Well, friction doesn't have to sort of do all of its potential. Okay, if very little force is being applied, then friction doesn't have to do, friction max technically doesn't have to do the full amount of what it's capable of. Okay, so although we say F equals mu r quite a lot, that only really applies when it's moving, okay, or when it's on the point of moving. So most questions say that things are on the point of moving. And we say that it acts in the direction opposite to where it sort of wants to move, or where it would move if the friction wasn't there. Okay, so we're just going to bring this in now, really, in some of the question types that we've been doing from before. So first thing we're going to do is try and draw a diagram from the information. So a box of mass 10 kilograms, so that's going to be 10G in the world of force diagrams, rests in limiting equilibrium. Okay, so this phrase here, limiting equilibrium, is going to be a guide that it's right on the point of moving. Okay, so that's actually quite an important phrase there, limiting equilibrium. On a rough plane, so a rough plane means we have friction 20 degrees above the horizontal. So what's this really going to look like then? Well, it's going to be one of these that we've seen quite a few times from before. We're going to have our box like this. We're going to draw 10G straight down. What will we then have to do? Well, yes, you might remember that we talk about breaking this up. Okay, so we'll almost definitely have to break that up there. What other forces will be there? Well, because it's on a plane, there will be a normal reaction, and R, it's the same R as in here. Now, are there any other forces? No. So if friction weren't around, the block would definitely go down, right? Because that's the only sort of parallel force. So it's definitely going to go down. So it means that I need to draw my friction facing this way. So people often like to write F, or when I know that I'm using F max equals mu r, I sometimes just write mu r there straight away. But that's basically what our diagram is going to look like. Okay, so let's go over now to like a neater version of that. Okay, so we've got R, we've got mu r, we've got 10G straight down. Let's do these ones while we're here. Well, this is opposite, so this must be 10G sine 20, and this must be 10G cos 20. So that's what my force diagram would look like fully complete. And find the coefficient of friction between the box and the plane. Okay, so our usual steps are that we sort of look at the perpendicular, okay, and the parallel. I'm hopefully quite fluent with those ideas now. So let's just break it into those different parts. So R is definitely a perpendicular. 10G cos 20 is a perpendicular. And we can set these ones equal to each other, okay? So R equals 10G cos 20. And you can pretty much always set the perpendicular forces equal to each other because, well, if R were bigger, it would be, lifting up and flying this way, wouldn't it? Okay? And if 10G cos 20 were bigger, then it would be breaking through, it'd be sinking through the plane, and you just don't see those situations in questions. So you pretty much always set R and this one equal to each other. Sometimes there's other forces as well, though, right? So sometimes, watch out, it might be another force there, there might be another force there, but just as a general rule, that works quite well. So the other thing we're going to do then is we're going to make our parallel forces equal. So that's mu r, and that's 10G sine 20. The 10G has been resolved, okay? So the 10G is done. So let's write that one down now. So mu r equals 10g sine 20. And that's because it was in limiting equilibrium. So that's why we're using mu r and an equal sign rather than, less than or equals or something like that. Okay. So how are we going to find mu? Well, there's a few ways you can do this. You could rearrange first. You could say mu equals 10g sine 20. That's a number. So this is all just a number divided by r. And then we could notice that that's 10g sine 20 over, what was it? R is 10g cos 20. So notice that the answer ends up being tan 20, which is a number which is equal to 0.36. Okay, so that's how you could do part A. Let's go back to the question and have a look at part B. So a horizontal force of P is applied to the box. Given that the box remains in equilibrium, find the maximum possible value of P. Right, so this is quite a bit more complicated. Well, the first thing to do would be to sort of refresh our diagram. So it says that there's a horizontal force. So let's just draw a horizontal force on. So that's going to be then something like this. I'm going to call that P. So how does that change things? Well, the 10g is going to stay the same. But what happens when you start pushing down more or pushing up and so on? You're going to find that R changes, okay? Because R means like how much the plane pushes back. Well, if you try sliding an object on a table, yeah, and you think about how easy that is, well, when you start pushing down and sliding it, it's changed, hasn't it? And the reason for that is R changes as other forces are sort of thrown into the mix. So what we'll have to do with P is we'll have to resolve it to make it fit this system of parallel and perpendicular, and then we'll have to look at our numbers again. In a nutshell, that's sort of what we're going to have to do. We'll get to the other bits in just a minute. So let's just look at our diagram first. So this would be our new diagram. So we'll go through and let's just write them down. So R, although R is still drawn the same, we've said that R is going to be a different value, okay? Or we should assume that it could be a different value. This will be the same because this is just the weight. Then we're going to have another one here, okay? Which is going to be, that's 20, so that's 20, like Z angles, yeah? And that's opposite, so that's why it's sine. So there's now three forces, yeah? Three forces there. Parallel, I've got this one. It's really, really hard to see. It's quite hard to draw this one, but the idea is that this one here then would be P cos 20, okay? And now the friction. Why have they drawn the friction like this? Well, let's work this out. So in our new situation, we've got kind of going up the slope and going down the slope, right? So it's not actually obvious that the block will go down the slope or it will go up the slope. We don't know which way it will go. So thinking about what happens to friction here is quite a bit more complicated. So let's go back to this question. A horizontal force is applied to the box. Given that it remains in equilibrium, right? Find the maximum possible value of P. Right. Well, if you want to make P a really, really, really big value, what we're doing is we're talking about when the particle here is about to go up, okay? So you might think that when it's about to go down and when it's about to go up are the same situation, but that's actually not true. That's not true because friction has sort of a threshold of what it can deal with. We're swapping the friction around because when it's about to go up the slope, P will be as big as possible, right? If it were any bigger, it would go up and it wouldn't be in equilibrium. The question still wants it to be in equilibrium. So if you want it to be in equilibrium, about to go up, you need the P value to be really, really big to go up, and you need the friction to act the other way. Because it's about to go up, because it's about to push up the slope, friction then is going to fight against you. So friction is always sort of the hardest one to place, really, because you've got to get into what's going on in the question, and that's quite difficult. Okay, so on this one, mu r is going to be another parallel force. Okay, let's read this note here. So if we increase P to its maximum, it's on the verge of moving up. So on the verge, limiting equilibrium. Okay, so the friction has to act opposite. Otherwise, it would just go up in this case. So what are our next steps after this one here? Well, they're the same steps as always. Okay, so we'll do parallel. So parallel is going to be, it's still equal, okay? So because it's not actually moving and it's in equilibrium, it's still going to be a case of doing equals. So up the slope, which is P cos 20, is equal to the forces down the slope. So notice that friction has changed directions. It's on the other side this time, okay? And then perpendicular R is equal to two things this time. There's two things going into the slope. And R has to be strong enough to deal with both of them. So R is actually going to be a bigger number this time, isn't it? Yeah? So P sine 20 plus 10G cos 20. Okay? So again, we've got our simultaneous equation situation. And what are we trying to find here? We are trying to find the maximum possible value of P. Mu. So mu, I did actually know mu. So mu doesn't change, okay? So in general, you're going to keep mu the same because it's like a property of how much friction there is between the block and the slope. So once you found that in a question, that doesn't change. So you're going to reuse that number there. So there's two things you don't know, R and P. So it's simultaneous equations. And if you rearrange, you should be able to get something like, let's do it back. So the way that they've done it is they've said that P cos 20 is equal to 10G sine 20, which is just a number, plus 0.36. And R is all of this business here. So that's just all gone in brackets. So P sine 20, P sine 20 plus 10G cos 20. And eventually you're going to get the things with P on both sides. So you're going to say P cos 20. When you've expanded this out, okay, you will then move it over to the side. So you'll say minus 0.36, minus 0.36 P sine 20 equals blah, 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 blah. You'll factorize from P, you'll get cos 20 minus 0.36 sine 20 equals lots of stuff. And then you'll just divide it, okay? I'm not going to go through that because it will make the video very, very long if I do that. But you end up with an answer of 82 newtons. Okay, so P being 82 newtons. So kind of difficult, that one, yeah? You've got to be able to first come up with the sketch for the basic situation, which I would say is part A. And then part B, we need to draw a new force. And the key idea is that as you're changing the forces here, R will change. And friction will often change as well. Weight won't change because it's the same box. And mu won't change in the question because mu is like a property of the friction between the materials in the question. Okay, so once you found mu, that's kind of it. This idea of maximum and minimum and so on, when you've got something like that, it's quite a good indicator that you have to do a bit more complicated reasoning about friction and what's going on, as you saw in this question here.